Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day, here in my virtual classroom. Step on inside, we are going to look at section 11.2 in the Big Ideas Math Integrated Math 2 textbook on areas of circles and sectors. We last looked at circumference and arc length of circles, and now we're in the area portion. A little more two-dimensional, and sectors are to area what arc length was to circumference. So hopefully this is nice. You probably need a calculator out for this one if you're going to follow along. And if you need to find that PDF, you can find it down below in the description section alongside timestamps. We're going to begin with the lecture, and then we're going to continue into the problem set, I think up to 45 problems or something like that. So let's go ahead and take a look at what they want to teach us. We are going to learn how to use the formula for the area of a circle. And you might already know that one, which is good. Find areas of sectors. Again, it's kind of a portion of the circle. And use areas of sectors. Don't know what that means yet. Maybe in a word problem kind of way. Or like pizza slices or something. I don't know. Geometric. Okay, we're going to do some probability stuff here as well, which is, nice. What's the probability it lands in this region? Probably dartboard questions will show up. And sector of a circle. Again, you've kind of seen that word a couple times now. Think of, again, sector. It's like an area's sector is like a circumference's arc length portion. All right, using the formula for the area of a circle. I think they're giving you kind of a basis for this formula here. You can divide a circle into congruent sections and rearrange the sections to form a figure that approximates a parallelogram. So if you cut these things up, you can kind of fold things on top of each other. Increasing the number of congruent sections increases the figure's resemblance of a parallelogram. So yeah, the more you cut this thing up, the more those thin slices aren't so curvy. The base of the parallelogram that the figure approaches is half of the circumference. So base is half of C because the other part must be the other part of C, right? Here are half of them and here are the other half of them. Half the circumference or half of pi times radius. The height is the radius as well. Yeah, any of these is the radius as well, like that. So the height is equal to r, so the area of the parallelogram is a is base times height, or pi times r times r, or pi r squared. Remember, this is kind of like an approaching that value kind of thing. It's as if it simulates it, and if it cut it up to infinite slices, that's a way to resemble and look at it. I very much like that one. Otherwise, they can prove it using calculus stuff, and we're not getting into calculus. So the area of a circle is pi r squared, where r is the radius of the circle. So if we have diameter, we're not going to be using that in a different formula. We will divide it by 2 and find its radius. So using the formula for the area of a circle, find each indicated measure. Let's find the area of a circle with a radius of 2.5 centimeters. And by the way, area is two-dimensional unit, so we'll be saying square centimeters and square feet and square inches and things like that. So find the area of a circle with a radius of 2.5 centimeters. Pi times r squared is pi times 2.5 squared. 2.5 squared is 6.25. You multiply by pi, you get 19.63. So once again, here's an exact answer, and here's the rounded answer. Looks like we're going to be using 2 decimal places again, nearest hundredth. 19.63 square centimeters. Let's do the same thing, only let's... The second question... Hold on, I just got an email. Let me see what this is. 1 second. All right, I'll address that one later. Part B, let's find the diameter. Okay, now we're going to find diameter of a circle with an area of 113.1 square centimeters. Because the area formula doesn't use diameter but uses radius, we'll find the radius and double it for diameter. So area is 113.1. That equals pi r squared. Now to solve for r, you need to do 2 things. Remember, pi is a constant. We'll divide by that first, get r squared by itself. Then we'll take the square root of both sides. So they're taking this value, they're dividing, I don't know what it's, apparently it's around 36, because the square root of this, you get around 6 here. Now, I'm never going to round early when it comes to stuff. I guess around 6 is probably like 5.999 something. But you double this value for its diameter, and you get 12 centimeters. Remember, it started off as square centimeters here, and then actual single units for length. Okay, probability. So, this happens actually... I skipped chapter 5, and I actually assumed this stuff would have been in chapter 5, but I guess not, but that was all statistics stuff. So if you know anything about probability, you divide your desired target by your overall amount of what you can do, and yeah, and they'll do it for lengths as well. I guess they're going to put them all together here. But probabilities found by calculating a ratio of 2 lengths, areas, or volumes are called geometric probabilities. So we might see some arc length things here as well. Using area to find probability. You throw a dart at the board shown. Your dart is equally likely to hit any point inside the square board. Are you more likely to get 10 points or 0 points? So the idea about your equally likely thing is you have no necessary skill here. It's not like you're going to work around the center. You won't miss the square, and every part has an equal chance of being hit. Every single part. Bullseye has an equal chance of hitting this part right there. Anyway. Are you more likely to get 10 points or 0 points? So you're going to throw a single thing here. So here is where you would get 10 points. 0 points is here. Basically, part of the question is which has more area. But the thing that we're going to calculate, because it's probability, is what is the probability of hitting either of these. So what we're going to do is we're going to take the area of the circle and we're going for the 10 points and divide it by the area of the entire dartboard. Then we'll take the area of those four I don't call them sectors, but those 4 regions and divided by the entire dartboard. And I'll show you how it works as the book will show you how it works. So the area of the smallest circle over the area of the entire board, the circle is a pi r squared. So pi times 10. 10, I can't tell if 10 is the, 10 is the number of points. 3 inches for the radius. Pi times 3 squared. And then the overall dartboard here, these are all just 3 inches. So 3, 6, 9, doubled is 18. So we have an 18 inch by 18 inch board here. That's why they're doing 18 squared. So the area of the whole thing's 324. We divide 9 pi by 324 and we get 0.0873. Now again, I haven't taught chapter 5 yet in this way that I did it, but 0.0873 also means you have an 8.73% chance of hitting the pink, the middle, getting 10 points. Probability of getting 0 points. Here's what you want to do here. You don't always necessarily add the areas of these 4 things. If there's a way that you can remove other areas instead, that would be preferred. So for example, we know the area of the entire square is 18, but the area of this circle, if it got cut out, if we cut out this dark blue here, you'd just be left with these 4 parts. 1, 2, 3, 4. So let's do that. I assume they're going to be doing that as well. They're going to be taking the area of the entire thing and subtracting the area of the big circle. I mean the yellow, green, pink combined, but pi times 9 squared. Pi times 9 squared there. And they're going to subtract that and still divide by the area of the whole thing. So 324 minus 81 pi all over 324. Looks like they did a fraction reduction before moving forward. But you get 0.215. Now this is a probability. That's 21.5% about, which means you are extremely more likely to hit this outer part and get 0 points than you are to hit the inner part and get 10 points, because this was around 9%, this is around 22%. So you could just calculate the areas and compare them, but when it comes to talking about probabilities, right there, more likely to get 0 points. Okay, finding areas of sectors. A sector of a circle is the region bounded by 2 radii of the circle and their intercepted arc. So this right here is a sector of the circle. It is a portion. It is a portion of the circle's overall area. As I've said before, just like an arc length is a portion of a circle's overall circumference. And it's the same thing when it comes to fraction, proportion, etc. In the diagram below, we see that sector. The ratio of the area of a sector to the area of the whole circle is equal to the ratio of the measure of the intercepted arc to 360. Yes, so once again, whatever your intercepted arc's measure is out of 360, let's say it's 90 degrees, a quarter of the circle, then this area is a quarter of the circle's area. That's how it works. We set up that proportion. Notice how they multiply both sides by pi r squared to get the area of the sector. That over 360 times pi r squared. So we can jump straight into that sometimes if needed. I'll be fine with that. Find the areas of the sectors formed by angle UTV. So UTV is a 70 degree central angle, which means this intercepted arc is also 70 degrees. But they say both sectors really here, so they have kind of options in what you can do. For the one with UTV here in pink, we're going to take the 70 degrees out of 360, and whatever that is, we're going to take that fraction of the circle's area. The circle's area is pi times 8 squared because its radius is 8. So 7 over 36 of 64 pi. And when you calculate it all, it looks like 39.10 square units. Oh, square inches. Now the other one, you have options on how you can do this second one. You can, 360 minus 70 is 290. So this is 290 here. You can do the same thing. 290 over 360 times pi, 64 pi. And you get this. You could have also subtracted the area of the circle, the 64 pi, from this, because whatever's not, we just talked about the geometric probability thing. Whatever's not this part is the rest of that circle's area. So we could have done 64 pi minus the 39.1-ish number. And apparently we would have gotten the same answer. So there you go. Let's keep going. Find the using the area of a sector. Let's see what they say about this versus the other. Oh, using the area to get maybe something else. I see. So find the area of circle V. If we have the area of the sector, we can set up that same proportion. Well, they have it as a, they're not doing the proportion version. I probably will, just keep myself sane. Whatever 40 is out of 360, and that's 1/9, the area of the sector is out of the area of your circle. Oh, they said find the area of the circle. So let me just call this area here. So from that setup, you can solve for it, right? I can multiply both sides by A, multiply by reciprocal, whatever, cross multiply and solve. In there, you will get, it looks like 315 square meters for that area of that setup. And remember, this reduces to 1/9. Finding the area of a region. Well, this might be a little bit like that dartboard question. We'll see. A rectangular wall has an entrance cut into it. Okay, here's the wall. I think this is the blue part. It's like an arch. You want to paint the wall to the nearest square foot. What is the area of the region you need to paint? So we need to paint this part blue. So paint is covered in two-dimensional units because it's a coverage of something. You do need area for that. So we need to paint the whole wall's area, the archway part. What we need to do basically is take the area of what would have been the entire wall without the entrance cut into it, and then cut out that entrance. And that entrance has like a composite portion to it. It's got this portion here. Looks like a square, 16 by 16. And then it's got a semicircle. And we got to find the areas of those, add those together, and take them out of the wall. Subtract that out. So that's going to be the plan. So the area of the wall is the area of the big rectangle here, minus the area of the semicircle plus that area of that square there. So we'll take that one out. Area of the entire wall, we got 36 by 10 plus 16, 26. Subtracting semicircle, half of the area of 64 pi. We say 64 pi because pi times 8 squared. That radius is 8. And then 16 squared, they said this is 16 here and that's 16 here. So add those together and take that out of this 936, product of those two. Get around 579.47 square feet of paint. I don't like that they rounded down though, because you just took out the 0.47 square feet of paint that needs that little part of the thing. I would have rounded up, just in general. It doesn't matter if it said 579.01. I would round it up to 580 square feet in that case, because you need more paint than less. Okay, some other monitoring progress stuff. Awesome. So there is some lecture. Let's move on to the vocabulary and core concept check before we hit the main part of the problem set. A blank of a circle is the region bounded by two radii of the circle and their intercepted arc. That vocab is called a sector. A sector of a circle, just like an arc length, is the portion of the circumference. I'll keep saying that. The arc measure of a sector is given in a given circle is doubled. Will the area of the sector also be doubled? Explain your reasoning. So this is interesting because, oh, well, actually, yes. I thought it was a different question. I thought it said the radius was doubled. The arc measure is doubled. Will this be doubled? Yes. It's all in proportion. It is all in proportion. Oh, boy. Let's think about it this way. Give me 1 second. I mean, I mentioned one. I guess I mentioned both. I mentioned a quarter circle and a semicircle. A semicircle is half its area. Well, a semicircle is half of 360 as well. It's 180 degrees. Quarter circle is a quarter of its area, and it's also a quarter of the 360 degrees. It's 90 degrees. They're all in proportion with each other, so yes. Now, they'll probably ask this later, and I know they've asked it once before in a way older unit. If the radius was doubled, the area of a circle actually is not doubled. It's actually quadrupled. And that's something we'll get into if we need to, but we'll see. All right, guys. So we are going to jump into the main core section. So find the timestamps of things you want. Print this thing out if you need to. Let's go ahead and take a look at what we're going to do. We are going to start with the numbers 3 through 10, where they asked to find the indicated measure. Kind of starts off the same way that the 11.1 did with like this set, or the basic set beforehand. All right, so number 3, we have a circle with a radius of 0.4 centimeters. We need to find its area. So the area of circle C is going to be pi times the radius squared. Now the radius is 0.4 centimeters, and we're going to square that. 0.4 squared is 0.16. So 0.16 times pi is an exact area in square centimeters. But let's go ahead and approximate that. I got to use the calculator for this one. I won't show you the calculator unless it's something that I really need you to see, the way that the order of something works, that kind of thing. And we're going to be rounding to the nearest hundredth, so 0.50 square centimeters. About half a square centimeter there. Looks good. Yeah, if there's something necessary I feel I have to show you on the calculator, I will. I just multiplied 0.16 by pi. Number 4. The area of circle C when the diameter is 20 inches. So the radius is half the diameter, which is 10 inches. I'm on the wrong type. 10 inches. So the area of this circle is pi times that radius squared, which is 100 pi. Yeah, I'll just write it there, which is 100 pi square inches. Now, what's 100 times pi? Well, I know pi is 3.14159, etc. So 100 times that's just a decimal shift. So it's about 314.159. 16 square inches. Okay, let's go to number 5, etc. These do not have diagrams. We want to find the area of a circle with a radius of 5 inches. Should be a quarter of this. No, it should not. Yes, it should. Wait. Yes, it should. Anyway, number 5. Sorry. Area is pi times 5 squared, which is 25 pi square inches. And yeah, it will be a quarter of that. I don't know. That must be... I can't do that in my head. So let's see. 25 pi be 70 something. 78.539. So 78.54 square inches. Number 6. Area of a circle with a diameter of 16 feet. So the diameter is 16 feet. The radius is half of that 16, which is 8 feet. Let's do area is pi times that radius squared, 64 pi square feet. And 64 pi is about, it's the calculator that slows me down. I don't know why exact answers aren't accepted here. 201.06 square feet. Feels like a little bit of drill and kill, right? You get some good practice on these with a diagram, without a diagram, with radius, with diameter. Let's find the radius of a circle with an area of 89 square feet. So 89 is pi times r squared. This is where we solve for r this time. So we're going to divide both sides by pi. Okay. So r squared is 89 over pi, and then we take the square root of both sides. We get the square root of 89 over pi. This was square feet, so radius will be in feet. That is an exact value. Let's look at the calculator for this one. So we're going to do square root of 89 over pi. And that's all inside the square root there. So that's 5.32 about. So about 5.32 feet. That is number 7. Number 8, let's find the radius of a circle with an area of 380 square inches. More of the same on this problem as well. So area, whoops, we know the area. Area is 380. 380 equals pi times radius squared. If we follow the same mold as we just did before, this should be the square root of 380 over pi. Divide by pi, take the square root. So I'm just kind of leaning right into that. Not square inches, just inches. So inches, and then that approximates to, this time I'll just whip it up really fast. So 380 over pi. 10.998, so that's going to be around 11 inches. Okay, that's how this thing rounds. Actually, I will show you that. I want to make sure you understand the rounding on that. 10.998, because the 8 is larger than 5. You kick this 9 up to a 10, and that carries this one over, and that carries this one over. You still write 11.00. A lot of people always get confused with that, going like, do I keep it as 10.99? Some people write 11, which is, I guess, fine and fair, but for precision, we are tending to precision. We're noting specifically that, well, it actually hits exactly, approximately 11. Number 9. The diameter. Let's find the diameter of a circle with an area of 12.6 square inches. So we're still going to use the area equals pi r squared bit. We'll find the radius as, once again, square root of this number over pi. That's in inches. And then the diameter is double that. So diameter is 2 radii. 2 times the length of a radius, I should say. So 2 times square root of 12.6 over pi inches. That's an exact. So let's go ahead and round that. I'll use the calculator there. So 2 times the square root of 12. I did 16, 12.6 over pi. 4.005. So I don't know if they were hoping that it was just going to be 4.4, like 4.01. But, sorry, I need to move this down. But I didn't round early. And in not rounding early, it's, for me, becoming 4.01. 4.00 would be imprecise. Imprecise. So that's the diameter there. That's why we do not round early. Okay, we do not round early. Number 10, let's find the diameter of a circle with an area of 676 pi square centimeters. I have a feeling that this one is going to be an exact answer because the pi is in it. I don't have to really divide by pi in the same way. So the area is, once again, pi. Oh, whoops, I know the area. The area is 676 pi. And this equals pi r squared. So yeah, the pi's cancel out when they divide. And we just got to take the square root of 676. And I've seen that. I think it's 26. Because 25 squared is 625. I'll double check that. But r is the square root of 676. Which is, it should be 26, I think. Square root of 676. Yeah, 26. So r is 26. That's 26 centimeters. So the diameter is double that, which is 52 centimeters. Exact. So we don't need to write the point something if there's no rounding to be had to begin with. All right, numbers 11 through 18. You throw a dart at the board shown. Your dart is equally, this is like the lecture stuff. Your dart is equally likely to hit any point inside the square board. Find the probability your dart lands in the indicated region. And I feel like, oh, maybe not. I was going to say, I feel like answering one will help us answer another. Maybe a little bit. It says yellow or green on one of those. Let's start with red. So the probability of hitting the red. So here's the idea. We're going to take whatever the area of the red circle is. That black dot, by the way, that's not another circle. That's just showing the center. Showing these are concentric and all that. But we're going to take the area of the red circle and divide it by the area of the entire dartboard, which includes the blue. So the area of the blue is going to be, let me write that first. Area of board is 18 squared, which is 324 square inches. So we're going to use that as our total pretty much each time if they're saying probability that. Unless they say something like given, some conditional, and they're not doing that. So probability of the red is going to be taking the area of the red over the area of the board. So the area of the red is 6 is its diameter. So this is going to be 3 inches. So when we do pi r squared, we're going to do pi times 3 squared. Pi times 3 squared, which is 9 pi. Keep that exact. 9 pi square inches. So the probability of red, once again, because we know the area of the board is 324, we're going to get 9 pi divided by 324. We'll use that and approximate it. It seems like they were using more decimal places in the lecture portion. I forget how many, like 5. I'll use those. And they didn't seem to be calling it a percentage after that. I'll say that out loud if you need me to, but hold on. 9 pi divided by 324. 0.87266. So 0.87, oh, 0.08727, I'll say. That's around 8.7%. 8.7%, that's what we're saying there. So the probability hits the red, around 9% chance. Getting in near that bullseye. This is a dartboard. All right. Number 12, the blue. Now the blue is just that outer region. It's not the entire square, and we saw something again like this before. We are going to take out basically the area of this yellow circle, and I mean everything inside of it. All I have to do is find the area of the yellow circle itself, but we take that out from the blue's 324, and then we'll be good. So the probability of the blue, I'm going to like write less scratch work as an overall. We're going to take the area of the entire thing, 324, and we're going to subtract the area of what would be the yellow. So its radius, how do we figure that out? Whole thing is 18. This thing is 6. So these are divided into equal parts here. These triangles, I guess they're kind of giving you a measure to show these triangles are congruent, given things with radii and stuff like that. So if 2x plus 6 is 18, then these are both 6 as well. So 6, 6, 6 in terms of inches, inches. Why does that matter? Because I'm trying to figure out the radii. Oh, well, 18 divided by 2 is 9. That works, but I'm sure we're going to have to use that 6 later for green. So the radius is 9, so pi times 9 squared. And this is going to be out of the same 324 we had before. So 324 pi minus 81. Excuse me, 324 minus 81 pi. I'm going to have to sneeze here. 324. Now I'm going to go to the calculator and type that one in. Make sure that you are wrapping that numerator around parentheses. So 324 minus 81 pi. And then divide that all by 324 like that. That should get us our probability, 0.21460. So 0.21460. About 21.4%. So again, we took out the yellow circle's region and we're left with just that blue part, and that's the probability as a whole. Number 13, probability of white. The white is just inside of that red region. Now, we're still dividing it by the entire thing, but we don't subtract it from the whole thing. Let's find the area of this, what would have been a white square. So the probability of the white, we're going to take the area of the white square, which is 6 squared, and then subtract the area of that circle, 9 pi, the red circle, 9 pi. So we're taking that out, and then you're just left with the white stuff, and divide it by, once again, 324. So 36 minus 9 pi over 324. I almost feel like reducing, and I probably should have done it on the previous ones, but I feel like dividing these by stuff. Like 36 over 324, I believe, is 1/9. But then you have to divide this by 9. I feel like I can reduce that. I think I could reduce this to 4 minus pi over, what's 324 over 9? 80, I don't know. It's probably easy enough. 36 probably, I think. Anyway, there would be that. But I'm going to use the calculator on that guy, so let me work that out. So 36 minus 9 pi. Remember, 36 minus 9 pi itself is just the area of the white. We divided by 324 for the probability. And we get 0.023844. 0.02384 is how I'm going to write that. Around 2.3%, very small chance. Even though everything's equally likely. I'm not going to aim for the white. Probability of the yellow. You might think that we found the area of the yellow before. Not quite, because the yellow does have stuff within. So the probability of the yellow, we do need to take the area of that yellow, but we got to subtract everything that's inside of there afterward. So I'm really looking at just this surrounding area, these two triangles, the two green triangles, and this white square. I know there's a red circle inside of it. That doesn't matter. It's just the region that's bounding all those things. We got to take those out. So we're going to take the area of the yellow. We did that before on this guy, that pi r squared, pi times 9 squared. So 81 pi is the region that the yellow has. Now we got to subtract a few things. We got to take the area of these two let's just start with the area of the square, the 36 plus, now there are two triangles, and this is going to be, you don't have to write it this way, but two of these triangle areas, and triangle area is 1/2 base times height, and here's where I was saying you don't have to write this, 2 times 1/2 is 1. So when we double the area of both of these triangles, we're going to get 1, but 1/2 of base, this base length is 6, times the height, which is also 6. Height has to be perpendicular to base, and base has to be one of your lengths, one of your side lengths. So 6 times 6. A lot of parentheses there. And divide that all by 324. Everything divides by 324 here. That's why I was keen on showing that earlier. So probability of yellow, we'll get 81 pi minus, and this will be 36 plus half of 6, 2 times half of 6 times 6, so 36. 36 plus 36 over 324. And once again, if I really worked hard at reducing the stuff, I would, but we're going to calculate it anyway. So 81 pi minus 72. You might notice that I'm not combining any of these things. Unless they both share pi in it, we ain't combining those. So let's go ahead and work that one out. I got my calculator ready. Let's do 81 pi minus 72 in parentheses, all divided by 324. And I'm trusting this 0.563175. So 0.56318, if I kick that one up. More than 50% chance, 56% chance that you hit that yellow. That kind of makes sense. That's a whole lot of coverage. But I took out that whole bit within the yellow. All right, probability of yellow or red. So yellow or red means that yellow portion that we already have, and the red, 9 pi. So probability of yellow or red. Did we find the probability of red? Oh, so we could do this. We could literally add the probabilities without needing to divide. Problem is I did round early. Even though it's 5 decimal places or whatever, I did round early, so I'm just going to take the areas that we have. So my yellow one is the 81 pi minus 72. 81 pi minus 72 is the yellow portion. The red will add with this. There's zero overlap with these, and the red that I have is 9 pi. So we'll add 9 pi to that. That's the red. And then we divide it by the whole. One or the other may be hit. No overlap. Because remember, the yellow took out the region that contained red. So now I could combine. I can now combine 81 pi and 9 pi, and I get 90 pi. So this is at least, even if I didn't reduce the fraction, at least I kind of combine like terms there, and I can type that out. So I'm going to type in 90 pi minus 72 all over 324. So this is 65% odds. So this is 0.65044. And it should be that I could have added this and this. You'll notice there will be a slight rounding difference, though. Notice how the fifth decimal is an 8, and this one's a 7. Those would have added for the last one to become a 5. This one is a 4. When it comes to precision, one slight bit, a 1/100,000th difference in numbers means I didn't attend to precision if I would round early like that and add those together. So the way that I did it is more precise. I know that kind of sounds, but it works. All right. Probability number 16, probability of yellow or green. Yellow or green. Now, remember the yellow, this is going to be kind of strange. I can do this one of two ways, but the yellow that I did, 81 pi minus 72, included the greens. Remember, this 36 was the 2 green areas here. So why don't we just take out that taking out? We'll just do 81 pi minus this 36. This was the area of the white square. So let's just do 81 pi minus 36, and then that includes this yellow taking this out, and we're now just left with the yellow and the green portions together. And now we're dividing by the 324. Once again, as these could have all reduced as fractions, I guess. 81 pi minus 36 over 324. 0.674287. 0.67429 by kicking that 87 into a 9. Two more, not blue and not yellow. So number 17, probability of not blue. Not blue means everything that's not blue. That basically means everything inside this yellow region. So we get to do all of that. So probability. Now listen, you have another option. I want to show that both should work here. So we can either do what I just said. Take the probability of the yellow. Not probability of the yellow. The yellow region That's 9 pi and divide by 324. Literally just, or not 9 pi, 81 pi. 81 pi and divide by 324. So that would give us 0.785398. So 0.78540. Another option could have been doing, remember, one it was 0.78 or whatever, 78%. You'd have to shift the decimal 2 places over. 100% is the number 1. If an answer is ever 1, that means 100% for the stuff. If I take 100% of what we have, the whole square, and take out the blue that we saw before, probability of not blue is 100% of everything minus the blue, and we have the blue as 0.21460. If I take out, and I know it's rounded, but we're only using one rounding value, and you know what we'll get? We'll get this number here, and I know this is technically rounded here, 0.78540. You can try in the calculator, but one or the other, if you found that one, it can totally work. That being said, I'm going to do that for the not yellow portion. So number 18, probability of not yellow, let's do 1 minus the probability of yellow, because I had to do a lot more calculations with that. It's not like I want to do, let's do the blue plus the green plus the white plus the, like that. Let's just take the yellow that we already found here, 0.56318, and I know it's rounded, but we're only using one rounding value within there, so we're good in a subtraction. So 1 minus that, 0.56318, and we're getting 0.43682. And that's, probably something you would have covered in Chapter 5 Biz. And with respect to statistics, sorry, this should have been here. With respect to statistics on the, not kind of thing, it's just I hadn't covered it. I hadn't done that chapter yet. Okay, let's move forward. Let's look at numbers 19 to 22. Find the areas of the sectors formed by angle DFE. Now, when they say sectors, there are two of them. There's that salmon-colored one and that blue one, depending on what your screen color looks like. You can call it pink, red, orange, whatever. I'm going to call it salmon. So with the 60 degrees, let me copy and paste this one over at least the first time. Then we can talk about what we're doing for future ones. So we have the 60 degree. We have the 60 degree central angle measure, which means the outside portion here is also 60 degrees. Do I have a color that's like that? I guess right here. Can you see that? That's a little light. Let's see if I can, give me 1 second. I'm pulling up a color wheel. I want to see if I can get that a little darker. Okay, well, it's kind of off salmon, but that's okay. All right, so whatever this 60 degrees is out of 360, your area of this sector is, I'll call it X. Your area of your sector is out of the area of your entire circle. The entire circle is pi times 10 squared. Pi times 100. 100 pi. 60 over 360 is 1/6. 1/6 is the same as the area of that sector out of 100 pi. So X is 1/6 of 100 pi. 100 pi over 6. You could write an exact answer of that, reduce it to 50 pi over 3. But, of course, they're going to have us, use calculator stuff. So 50 pi over 3 also reduces to 50, or rounds to 52.359 or 52.36 square inches. That's the area of that one sector. Now, the area of the second sector, you have two options. This first time I'll present it with both. After that, I might be versatile and just do one or the other. So in this next one in blue, you could also figure out that this central angle is 300 degrees, which means the measure of the arc is 300 degrees. So 300 over 360 equals, let's call this y. This y over 100 pi. And then this leads us to this reduces to 5/6. We're going to take 5/6 of 100 pi. So 5/6 of 100 pi 500 pi over 6 or 250 pi over 3. And let's see what that is. Significantly bigger. 261.799 or 261.80 square inches. Now, these two added together should be the area of the entire circle, obviously with maybe a little bit of rounding error to the nearest hundredth. But these two together should be the entire circle. Let's do this in our head. 261.8 plus 52.36 is 314.16. I'm going to go in the calculator and see what 100 pi is. Oh, duh. It's 314 now 159, right? 314.16. So those two added together are that. What's my point? My point is that I could have taken the area. Take the area of the entire thing. I said this in the lecture portion. I could have taken the area of the entire thing minus the area that we already found, right? 52.36. You could even say this part right here. Notice this is 1/6 of 100 pi. This is 5/6 of 100 pi. So straight up from there, I think what I'm going to do, I'm not going to use that version. I'm going to just take out the fraction that's not, because both of these are ultimately the entire circle, the salmon and the blue. So if we find the area of 1, I'll subtract the fraction. If this is 1/6, this will be 5/6. If this is 3/7, I'll make it 4/7 if the fraction is nice and clean. All right, let's go to number 20 with that in mind. Here we go. Number 20, we now know, I'm going to start with the blue this time, and I'm just going to use the diagram that's there. Whatever 256 over 360 is, and I actually don't have a quick fraction reduction in mind yet, but whatever 256 over 360 is, this, the only thing I'm going to use here, this x is out of pi r squared. This radius is 14. So, what is that? 256, divide them by at least 4, 90 and 64, 64 over 90. Divide that by 2, 32 over 45. 32 over 45, is that as much? I guess as much as I can reduce it. So 32 over 45, x equals 16 pi times that. 32/45 times 16. That can't reduce more, right? I don't think it can. So 32/45 of not 16 pi, that's not 4 squared, that's 14 squared. 196 pi. That would have been a way different answer. So that's about 32 over 45. Hold on, first let me make sure those are the same. 32 over 45 is 0.71, and the ones are repeating. And 256 over 360 is also that. Okay, that's right. All right, times 196 pi. 437.868. So 437.87 square centimeters. Now to find the next one, that salmon color one I was going for before, 32 over 45, 1 minus 32 over 45, I should say, is 13 over 45. So this time we're going to find y, this area of this guy, just by doing 13/45 of 196 pi. It's the other part of the area of the overall. The other angle must have been 104 degrees, but that's what it reduces to, 13/45. So 13/45 times 196 pi. Okay, 177.883. So 177.88 square centimeters. Okay, number 21. I don't think this fraction will reduce. 137 feels prime. I don't think that one reduces. Whatever. 137 is out of 360, and I'll leave it like that. This x, let me use those colors. Hold on. Let me bring this back. This x is, shoot. Actually, here, let's do this. Now we understand the proportion aspects, I hope. We can probably go straight into it. This x, I know we're kind of changing what's x and what's y, but this x is 137 over 360 times the area of this guy. That's pi times 28 squared, pi r squared. So I'll kind of let the calculator do that right now, but I'll tell you that 28 squared is 784. So let's remember that for the next one. Pi times that times 137 over 360. So that's 937.31 square, my calculator's covering it, square meters. Square meters. Now, the next way I'm going to do the blue is actually just as fast as anything else because there's no fraction to reduce. I guess at this point they're all the same anyway, if you don't reduce the fraction. But 360 minus 137, I don't want to be wrong. So I'm just going to put this on 137 is 223. So this y, if you will, is 223 over 360 times that. That was 784, I believe. 784 pi. Yeah. So 223 over 360. $1,525.697. So 1525.70 is what that would round up to. Okay. Last one of this set, number 22. The salmon. Salmon-esque. We got, hold on, 22. I'm trying to change colors. Okay. 75 over 360. X is going to be 75 over 360 times 4 pi times 4 squared, 16 pi. That does reduce. At this point, I'm going to just keep it. It's not, if I'm not writing an exact answer simplified, I think at this point, we'll just keep it this way. 10.471, so 10.47 square feet. Sorry if I'm not labeling the things X and Y inside of the thing. Hopefully you're recognizing what I'm doing by color. You can call it different things. It's just the book will say area of, arc DE, sector DE, or whatever they call it, DFE. So I'm not doing that whole thing. So Y, 360 minus 75 is 285. So we're going to do 285 over 360. And literally that's the degree. So I guess I'm not really doing it faster than the book is. And the book would have been if I'm not reducing the fractions. So 285 over 360 times 16 pi. 39.793. 39.79 square feet. Okay, let's get to the error analysis. Describe and correct the error in finding the area of the circle. Number 23. Don't want blue. Number 23. It looks like the diameter, this was kind of an error in the last one as well. It looks like the diameter is 12, but the area should be pi r squared, not pi d squared. They incorporated the diameter into the area of a circle formula when it should have been radius. Now it does look like they have, they do round it to the nearest hundredth. A mistake would be to take I know that the radius is diameter divided by 2, so a mistake would be to take half of that area though. This will not be half of that area, and I stated this before. This will be a quarter of the area. Your answer is going to be closer to 113 something. So the radius is 6 feet. Because you're squaring 6, you get 36 instead of 144. It's 4 times smaller. So area is pi times 6 squared, which is 36 pi. I don't know if we actually saw that number before, but I'm going to use it right now. I said around 113.9 something. Whoops, it's typed 6 pi. 36 pi. 113.097. So 113.10 feet. Square feet. So yeah, it's not half of the area, and that's something else that I think someone might make a mistake doing. Number 24, describe and correct the error in finding the area of sector XZY when the area of circle Z is 255 square feet. So they don't give you radius stuff, they just give you the area straight up. We can work off that. Let's see how they wrote it. They said whatever n is out of 360. What do they want? Finding the area of sector xzy. So I guess that little n is kind of what they're calling here, right? So whatever n is out of 360, 115 is out of 255. Looks like they gotta have the thing swapped. So n, okay, I'm gonna put the 115. I'm gonna write the correction first, and then I'll identify their error. Whatever 115 is out of 360 is what they need to do. The degrees with degrees. The proportionality needs to have corresponding parts correct. N is the area of the sector, and we're dividing by the area of the entire circle, 255. So this is how our setup is going to actually function. Their proportion does not align corresponding parts. Swap denom values or numerator values, either or. I think I actually swapped the numerator values. So that's going to be our setup here. So let's keep solving by multiplying by 255. Again, things could probably simplify, but 115 over 360 times the old 255. Let's figure that out. And it does change things when you get to this stage. 81.458, so 81.46. Notice they got 162, whatever. It looks like they got basically double what I got, almost. Doesn't look like it's perfectly doubled, so I think that was just a coincidence. But square feet. I guess they, oh yes, square feet for 255, yes. All right, so that's 24. We still have quite a bit to go here. I think over 20 problems. Number 25. In exercises 25 and 26, the area of the shaded sector is shown. Find the indicated measure. So this time they give you sector. We're working off that. I'll still build the proportion stuff from before. We need to find the area of circle M. This part's 50 degrees, which means this other part is going to be 310 degrees. Remember, they got to add to 360. So whatever 310 is out of 360, 31 over 36, whatever 310 is out of 360, the area of that shaded sector, 56.87 square centimeters, is out of the entire area, which we got to find. So I'm going to multiply both sides by A, and then I kind of take the reciprocal of this thing multiplied, right? I did this a lot with the circumference once before. I want to kind of save that time. But we're going to multiply by 360 over 310 or 36 over 31. Little fraction reduction for myself. Multiply both sides by A, multiply both sides by the reciprocal, area gets by itself. So this will be 56.87. I mean, the rest is algebra, right? My goal is to set up the geometry with you and ensure that my answer that I get afterwards correct. And I'm getting around 66.04. I was going to make sure that we're getting area. 66.04 square centimeters. Now it should be more. It should be more than 56.87, but not much more. Because all that's left is that 50 degrees, that fraction, that 5 out of 36 that wasn't included. So it's not much more, but it should be more. Number 26, radius of circle M. To find the radius, we need to, well, I can just rewrite that area instead as pi r squared. So when we find that area, we'll solve for r within that. So the radius of circle M, we have whatever 89 is out of 360, right? The area of the sector, 12.36, is out of this pi r squared. R is unknown. R is what we're trying to solve for. So this time, I'm going to do a little more algebra work with you guys to show how I'm getting r by itself. I'm going to multiply both sides by r squared. I'll leave the pi there. And then I'm going to multiply both sides by that reciprocal and just show you where everything is. Times 360 over 89. So ultimately, r squareds are gone here. Pi stays. 89s are gone. 360s are gone here. And I'm going to take the square root of both sides, right? This is still an r squared. So r will equal the square root of what's inside. Numerator, we still have 12.36 and 360. Denominator, we have 89 and pi. So a couple things involved. I'm definitely showing you this portion on the calculator to see what we are going to get here. So on this, you want to do square root of. Now, I'll just type 12.36. Wait, that's fine. 12.36 times 360. And I got to divide this by, here's where I got to use parentheses, 89 pi. I think I've stated this before for the circumference stuff, but make sure that that pi is not being multiplied in the numerator. It's actually a denominator value, and I'm taking the square root. 3.989, that's around 3.99 meters. So there we go, 3.99 meters for the radius. Very close to 4. I would have imagined they would have wanted 4, but they probably couldn't get perfect on it. Change the problem, dude. 27 to 32, we're going to find the area of the shaded regions that we have. The blue is considered the shaded for all these. I don't know if I have to copy paste these diagrams over. This is probability stuff without the probability. So we don't have to divide by whatever the whole is. So when it comes to shaded regions, we got to, take, these are concentric circles from that center. We got to take the area of, one over the other, minus the other. So area of the whole thing, we're going to do pi times 24 squared, the area of the big guy, minus pi times 6 squared, the area of the small guy. Those are their radii, respective radii. Here's where I'm probably going to do some more exact answers to begin with. 576 pi minus 36 pi. I can combine those, and I can get my 540 pi square meters exact answer. Now I'll calculate 540 pi. Because I don't have to reduce any fractions or anything, I think that'll be fine enough. And I'm getting 1696.46 square meters. That's number 27. Number 28. Here's the thing. This is just 4 of the same. Like, they show the congruent. They show these are congruent radii. It's just 4 of the same thing repeated over and over. So if we find the area of just one of them, let's just quadruple that entire set. So I'm dividing this into kind of quarters so you understand why I'm going to multiply whatever I do by 4. So like that. I'm trying to make it look nice. This is for you. This is for you. I want it to look nice for you guys. All right. So the area of this one, I'm going to do 4 times whatever the heck I do inside of there. Now, what am I going to do inside of there? 20 by 20 squared. That means each of these are 10 inches. I want the area of one of those squares. So 10 by 10. 10 squared minus. Now, if that's 10 inches, this radius is 5. Half of 10. So pi times 5 squared. And you take out that square, you take the circle out of the square, you have one of those blue sets, but you got to quadruple whatever you have. So the area is going to be 4 times, I got 100 minus 25 pi. That's not 75 pi. Notice this one had pi's in both of them. This is separate. So unless outside of distribution, which I'll do, 400 minus 100 pi, because I'm sure there are other ways you could have gotten that answer. Square inches, excuse me, not meters. Outside of that, that's the exact answer. All that's left to do is use the calculator. So 400 minus 100 pi. It's 85.84 square inches about. So again, found the area of one of the small guys with the blue stuff around it, then quadrupled it because there are 4 of those. Number 29, very interesting. We got to find the area of these, and they show incremental widths of 1 foot for each of those. Let's make sure we don't kind of make mistakes in what we want to do. Notice they're white inside here and here. So it's just this blue one and that blue one there. We can basically add the areas of both of those. If we find this one minus that, and then we find this one minus that, we'll just add the result. Remember, if I say white area versus white region or something like that, those are 2 different things. So let's just consider this a bigger one and a smaller one. I'll put a B and an S. So the area of the B, area of the bigger one, as these are all ones, 1 foot, 1, 2, 3, 4, 5. There are 5 of them. So that radius is 5. So pi times 5 squared. Now we got to take out the area of the white region within there. That's just anything inside there. That's pi times 4 squared. And that'll be 25 pi minus 16 pi, which is 9 pi square feet. So that's the area of the big. The area of the smaller arc strip thing, whatever, that's a radius of, I think, 3. 1, 2, 3 feet. So pi times 3 squared minus pi times, and then the other one's 2 squared because there are 2 white circular regions, but we're going to take both of those things out. or circles, I should say. So that's 9 pi minus 4 pi, which is 5 pi square feet. Ultimately, we're going to add these two. We're going to take that one disk minus the other disk, or plus the other disk. So area total is area big plus area small, no overlap, which is 9 pi plus 5 pi, 14 pi. That's exact. Let's round that. 14 times pi. 43.982. 43.98 square feet. All right. Number 30. You have options in which way to go. It's this blue region here. We can either take the area of the whole blue region and divide it by 2, or take the area of half the circle and subtract the area of half that circle. I'm going to do the first option. I think it makes sense. Let's find the area of the whole thing, and then let's just take out a half of it. Let's divide it by 2. So, because we can tell it's half, 180 degrees diameter, all that stuff. These are each 8 centimeters, so the whole thing is 16. So the area of what would be the original blue, I can't just call it blue. Whatever. I'll call area of disk. Area of disk, and that'll do area of blue, is 16. Pi times 16 squared, which is 256 pi. Now we got to take out, minus, I missed this part, minus pi times 8 squared. So that's 256 pi minus 64 pi, which is 192 pi square centimeters. So that's the area of the disk. The area now of the blue itself, the shaded, will just be half of that. Half of 192 pi, which is 96 pi square centimeters. So that, rounded to the nearest tenth, is 301.592, 301.59 square centimeters. 2/3 of the way through. Let's go to number 31. We need the area of the shaded region. Basically, let's take out the area of that triangle, but we got to figure some things out within there. Let's see if I can walk you through this. I'm going to try and do it as math savvy as possible. This thing here is 5 inches. This is a right triangle, and with this being a diameter and that being a radius here, that means all these sets are congruent. If these are congruent, that means that you're in a special kind of triangle here. In fact, let me do this. I'm going to copy and paste this one over. Listen, there's probably more than one way to come up with this answer, especially when it comes to, well, we haven't done areas of segments before, and they didn't really teach it. But I just got to take out the area of the whole triangle set. So here's what I have. These are congruent. But congruent right triangles, this is a 45, 45, 90. And in a 45, 45, 90 triangle, this has a 1-to-1 to root 2 ratio relationship, where this is the root 2. If I divide by root 2, this length would be 5 over root 2. 5 divided by root 2, or 5 root 2 over 2. I don't know which one's easier to state as an overall. Probably 5 root 2 over 2, because here's the thing. If I want to find the area of the entire triangle, I should do, this is also 5 root 2 over 2. I don't know which one is better to say. Let me just say 5 over root 2. I think if I need to simplify at the end, I will. So I'll call this 5 over root 2. This is also 5 over root 2, and this is 5 over root 2. It's just cleaner to write. So the area of the triangle, let's start with that. By the way, we needed to find these things out for the radius as well. The radius of the circle, the pi r squared stuff. We totally needed all of that. I was just doing it for the triangle. So this is 1/2 base times height. Now the base is 2 of the 5 over root 2. So that's 10 over root 2. Not 10 over root 4, nothing like that. And the height is 5 over root 2 there. So 1/2 base times height. So that is 1/2 of 50 over 2. Ultimately, it's 50 over 4, or 25 over 2. Square inches. Which is 12.5 square inches. Okay, there's the area of the triangle. The area of the circle is pi times the radius, 5 over root 2, this is why I said this is going to be fine, squared, which is 25 pi over 2, or 12.5 pi. So the area of square inches, the area of the shaded, or the blue, is going to be 12.5 pi minus 12.5. And don't say that that equals pi. So 12.5 pi minus 12.5. Assuming all went swimmingly, it's going to be around 26.769, 26.8, no, 77. 26.77 square inches. Feel pretty good on that one. I mean, as an overall, I guess trig is another offering that you can do on that, but you know, the whole goal of this is to, I don't know, use what's available to you, and I don't think I want to use trig on something like that and round kind of early. I like the root 2 stuff that we could use, because notice how every time you squared it, something kind of cleaned up in a way that was really nice for us. It was quite good. All right, last one in this set, number 32. We have, okay. I probably want to bring this one over as well to mark some things up. We do once again have to find the radius. Whether we're finding areas of the triangles and all that kind of stuff, we still have to find that radius. Now, these triangles are congruent in every which way. We have a side case to show the triangles are congruent. They show that these two sets of parts are congruent, so this is also 3 meters, 4 meters. Basically, take the area of one of the triangles and double it. Now, the other part is this is a diameter. This is an inscribed angle. An inscribed angle to a semicircle intercepted arc is going to be a right angle. That makes this a right triangle. If this is a right triangle, 3 squared plus 4 squared equals, boom, the diameter is 5. Diameter is going to be 5 meters. You can use Pythagorean theorem to figure that out. I've mentioned 3, 4, 5 triangles way too often for me to need to really mention it again. If that's 5 meters, then the radius is 2.5 meters, 2.5 meters. So we are going to do the area of the shaded as the area of the circle minus the area, two area of triangles. So the area of the shaded, area of the circle is pi times 2.5 squared, pi r squared. Now 2 of the area of the triangles. Here's the area of the triangles. 1/2 base times height. You have to remember height is perpendicular to your base, so whatever base side length you choose as base, I can choose 4, for example, height can be perpendicular like this 3. So I'm not going to do base is 5 and height is, oh man, now I have to find this height. I don't want to deal with that kind of similar right triangle stuff. We don't have to. We can use the 4 and the 3. So 2 of the 1/2, which will cancel out, times 4 times 3. So 2 times 1/2, boom, gone. And you're left with 4 times 3 there. So ultimately, the area of shaded is going to be 2.5 squared is 6.25. So 6.25 pi minus 12. What's my calculator? 6.25 pi minus 12. I'm getting about 7.634. Oh, this was in square meters, by the way. 7.63 square meters. And that's number 32. All right, number 33, problem solving. The diagram shows the shape of a putting green at a mini golf course. One part of the green is a sector of a circle. Find the area of the putting green. So you do have some congruent marks here and the right angle, and this right angle stuff right here. This is also right angle. I have a bunch of right angles. So you're looking at a square here, which means this is also congruent, and rectangle with that's congruent to that. That means that's congruent to that. A lot of ways I can solve for x automatically. It looks like I can set these two things equal to each other. Let me start off with that before really diving into anything else. So on number 33, I know that I can automatically say 3x minus 2 equals 2x plus 1. It doesn't equal 5x, right? It's not that, but equals 2x plus 1. Use that to solve for x. Subtract 2x, add 2, we get x equals 3. So we're going to get a bunch of lengths here, and then let's utilize those lengths thereafter. If I reestablish this diagram, I'm going to wipe out those measurements that you see here and come up with what they are now. So let's wipe these things out. 3x minus 2, 5x, and 2x plus 1. And we're now going to see them as 3x minus 2. 3 times 3 minus 2 is 7. So that means that's 7. You could double check that. That should work. And 5 times 3 is 15. Okay, so when it comes to these things here, let's add these different areas up to get the composite figure. 7 by 7 is going to be 49. 7 times 15, this base times height is going to be 105. Let's find the area of this sector. Now that's a 90-degree angle here as well, which means it's a quarter of a circle. Which means, this would have been a bigger circle like, not like that. This would have been a bigger circle like this with a radius of 7. So this is 1/4 of pi r squared. Pi times 7 squared is 49 pi. So 1/4 of 49 pi. Ultimately, the area of the total thing is going to be 49 plus 105 plus 49 pi over 4 square feet. If you want an exact, that would be 154 plus 49 pi. Let's write 49 pi over 4 as whatever that 49 over 4 is 12.25. So 12.2, I should have known that. 12.25 pi square feet. And then let's go to the calculator for the whole thing. Times pi plus 154. Does 49 plus 105 is 154? Yes. So 192.48451. And I don't think that's... I was going to say, I don't think that's rounded. I guess it must be rounded if pi's in there. It's just it cuts off. I know you're not looking at it. I don't know why it cuts off here significantly more than it does there. I guess we're going to round. So area is about 192.48 square feet. 192.48 square feet. So a lot of things involved there. The area of the sector was taking 90 out of 360. That's 1/4. And we're taking 1/4 of the area with the radius of 7. That would have been 49 pi to get that going. So that should be panning itself out. Should be good there. Let's jump to... I lost my page. Jump to number 34. Making an argument. Your friend claims that if the radius of a circle is doubled, its area doubles. Is your friend correct? No. So I've stated this a couple times here. I was going to type the letters N-O, but I think I'll write it. Explain your reasoning. I'm going to show you mathematically why this doesn't work. If you have a radius of r, then the area, I'll just say small, is pi times r squared. If you double that radius, then the area of the bigger one is pi times 2r squared. What happens when you square 2r? You get 4r. So pi times 4r squared, which is 4 pi r squared. It will be quadrupled. It will be quadrupled. You have to square the increase in that ratio. You have to square it. This is a two-dimensional figure. The r is being incorporated twice into it. So if you make one 6 times bigger, the radius 6 times bigger, the area will be 36 times bigger. Unlike circumference, which does stay the same. Which does stay the same as circumference. So I have mentioned that a couple times. This is where they bring it up. They might bring it up in future problems. Not as a question, but to solve a problem. We can probably use that now. Number 35, modeling with mathematics. The diagram shows the area of a lawn covered by a water sprinkler. What is the area of the lawn covered by the water sprinkler? So we got a 15-foot radius, 145-degree central angle. Whatever 145 is out of 360. This area, find the area of the lawn. This area of the sector, I'll just call it A, is out of your pi times r squared. We're going to multiply both sides by this thing here. So that area, I'll call it sector. Area of the sector is 145 out of 360. I won't bother reducing. Times 225 pi. So 145 out of 360. 284.71 square feet. That's part A. Part B, the water pressure is weakened, so the radius is 12 feet. This goes right off of 34. So it's weakened to 12 feet. What is the area of the lawn that will be covered? I'm not going to plug this thing in this time. I'm going to answer it in a different way based off question 34. This new ratio here, you have shrunk the radius from 15 to 12. So 12 over 15, listen, that's 0.8. You're 80% of what you had before. Actually, I won't say, yeah, I'll say 0.8, that's fine. It's 4/5. 4/5. 4/5 of what you had before. Is the area of the new one going to be 4/5 this area? No, you have to square 4/5. You have to square 0.8. So this squared is this squared, and 0.8 squared is 0.64. This is your area ratio. The area ratio. That's not the answer. But you will need to take not 80% of this value, but 64% of this value. 284.71, and I have the other value in my calculator because this is rounded. So the area here is that times that. So in my calculator, this is the way I'm going to do it. If you want to do it the other way, you can. I just wanted to explain and show that this is how this works. So let's take this area and multiply by 0.64. Take that, and we get 182.21 square feet. And yes, if I did 144 pi and did that exact same thing, I'd get that exact same answer. But they banked it off of the previous question. So I want to incorporate that very nicely. Okay, let me get a water break here. Okay. Number 36, modeling with mathematics. The diagram shows a projected beam of light from a lighthouse. So this is a top-down view, and the light goes this way, right? I was trying to think. Maybe it goes fully around, I guess. What is the area of water that can be covered by the light from the lighthouse? Whatever 245 out of 360 is, the area of this sector, I'm calling it X this time, area of this sector is out of the area of the entire thing. So listen, nothing's changing in what we do. We're just using word problems to answer the same kind of question. Pi r squared. So X is going to be 245 out of 360 times 324 pi. Multiplying both sides by that guy, and that's what 18 squared is. So 245 out of 360. I'm not want to be reducing fractions anymore. If they don't want me to, if they don't want exact answers, they don't need them. They don't need it. 692.72 rounded. 692.72 square miles. Oh, geez. Lighthouse is stretch, man. Oh, I'm sorry. This is square miles. Square miles. Not just miles. So 18-mile radius. Still, that's pretty good. What is the area of land that can be covered by the light from the lighthouse? So, we kind of did this before. We do 360 minus, this is part A. We do 360 minus 245 and get the rest of it. So 115 degrees. So let's do the same thing. Let's call this Y, and we'll do 115 out of 360 times 324 pi. You could also subtract this from 324 pi, but I'd use the exact number that you had in your calculator before. So let's do that. 115. So this isn't very thought-provoking. It's just kind of doing these things. 325.15 square miles. I hope I'm not making any little mistakes on something I type in or whatever, but that should be good. Or misinterpreting the question. Okay, number 37 and 38, we will analyze relationships. Number 37. Look back at the perimeters of similar polygons theorem and the areas of similar polygons theorem in section 8.3. That's when we learned it, section 8.3. How would you rewrite these theorems to apply to circles? Explain your reasoning. Well, the theorems, the idea is that the ratios, let me just write this, perimeters of similar polygons theorem would basically state that, I'm just doing this off the top of my head, the ratios of perimeters of similar polygons is equal to the similarity ratio, or the ratios of sides, I'd say similarity ratio, of the two polygons. So it's equal, right? They're equal lengths. Now, this is akin to circles. This is akin to a circle's circumference. Let's say a radius, diameter, circumference, arc length, or arc measure. Central angle measure or arc measure. It will be equal. What I mean by this is if, hold on, I want to put a period here and fit it on this line. No. Okay. If you doubled something, if you doubled the radius, the circumference will be doubled, any arc length will be doubled, the central angle will be doubled, arc measure will be doubled, things like that. All of them will also be doubled. They'll be equal. So let's apply that now to areas. Kind of writing a lot. Instead of perimeters, I gotta sneeze. Maybe not. Areas of similar polygons. That ratios of areas of similar polygons is equal to the square of the similarity ratio of the two polygons. So I've kind of mentioned this several times now, how this works. If I double a radius, the area of something will be squared. So this is akin to a circle's area or sector. I think that's all I have to say. So doubling a radius or a diameter or an arc length or something like that will quadruple your areas and stuff. So that's how that stuff works. That's how that stuff works. So yes. Number 38. A square is inscribed in a circle. I might want to draw that. So I got a circle. And I got a square inscribed in it. Square is inscribed in a circle. Number 39. Just kidding. Draw it. Okay. The same square is also circumscribed about a smaller circle. Oh. Well, good thing I just made a center. Close enough, I hope. Close enough. Indeed. Okay. They're going to ask what the ratio are of these two circles, aren't they? Draw a diagram. Okay, I did. Then find the ratio of the larger circle to the area of the smaller circle. Okay. Well, here's the thing. The radius of the smaller circle, if it was x, then the square's length would be 2x there. Let's see. I need the radius of the larger circle. The radius of the larger circle. See, this is one of those. How do I put this? If this is x, I'll do this in green. If this is x, this is a right angle. This would also be x. That's just square property stuff. So this is x times the square root of 2. So the radius of the larger circle is x root 2. Now, the similarity ratio is, did they say, the larger circle to the smaller circle. So it's x root 2 over x, which means square root of 2. So the ratio of areas takes the similarity ratio and you square it. What I like about these problems is they're connecting one to the other. So it's 2. So to find the ratio of the larger one, it's going to be 2. There it is. This circle's area, I know you might not be able to see it. I know you can't necessarily tell. You say, this doesn't look like it. I don't believe it. It's true. It's the way that it bends around, how much more there is. This circle's area right here and everything inside is twice as large as this circle's area in here. Basically, the purple and the yellow are equal in area right now. Those are equal areas. All of yellow can fit right inside that circle perfectly if you do things right. You need the same amount of paint. with that setup. Again, the radius of this circle was x. The radius of this circle is x root 2 based on that special right triangle, the 45, 45, 90 triangle we have. Okay, I think 7 more problems. Number 39, construction. The table shows how students get to school. 65% take the bus, 25% walk, 10% other. Not a lot of parents driving them to school, or them driving themselves. Explain why a circle graph is appropriate for the data. You can make a pie chart. So it's part A. So a pie chart, I guess I'm going to have to make one later. So a pie chart can be made to discover central angles. Can be made with central angles representing percentages. Yeah, sounds good. Part B, you will represent each method by a sector of a circle graph. Yeah, so we'll do that. Find the central angle used for each sector, then construct the graph using a radius of 2 inches. Okay. So let's kind of do like a center, and then let's kind of do like a circle, and then let's kind of do like a pie chart. When I said pie chart, I hope you know what I meant by that, because they never say that phrase. So let's do 65%. Oh, well, these aren't degrees though, right? These are percentages. So 25% is a quarter of a circle. That's 25, right? 10. Whatever. By the way, does this add? Yeah, this adds to 100. So 25, let's see. What would be 90, 45, a little more than half, about probably 25 like that. So 65 is like everything else. Oh, 10, excuse me, 10%. So here's a quarter, here's like 12 point whatever. So 10% might be something like that. So 65 can be everything else. I know it's hard for me to imagine kind of what that's supposed to look like now, but now I'm going to come up with it. So 25% walk, 10% other, 65% da bus. It's a lot of bus business. Find the central angle to use for each sector, then construct the graph. So the central angles, you got to take these percentages of 360. So I'll probably rewrite this stuff, if that's okay. But 0.65, 65% is 0.65. I can do 0.65 times 360. 0.25 times 360, or a quarter of 360. We know that one. That'll be 90. And then 0.10, we should know this one as well. 0.10 times 360. In fact, I'm going to not use the calculator at all. I know this is 90. I know this is 36. So this will be 360 minus the sum of 90 and 36. 360 minus 126, which is 234. These are degrees. These are degrees. Boom, boom, boom. Bang, 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 bang. So that gets us central angles, which means it also technically gets us arcs. So we know that this is 90 degrees, this is 36 degrees, and this here is 234 degrees. They said, construct the graph using a radius of 2 inches, find the area of each sector. So let's call this 2 inches, which has nothing to do with the percentages themselves, it's just how big the sectors are. So the area of each sector, the area of the bus folk is 234 out of 360 times pi r squared. I'll just call it 4 pi. 234. See, the thing is, though, that's 65%. Like, okay, so here, I'm clicking this on my calculator now. Let me go to it. That's the 0.65 again. So we're going back. They said find the central angles. I'd rather just use those numbers. We got to take 65% of 4 pi. We got to take 25% of 4 pi. I know that answer. And we got to take 10% of 4 pi. And I should know that answer as well. So this is the only one that's kind of like, yeah, we'll figure it out. But 4 pi, I guess we're not going to do in terms of pi though, right? So at least I still got to write that out. But 8.17 square inches. So there's the first one. So it's kind of almost working backwards now. The area of the walkers, area of those who walk, not how much they walk in area, that is a quarter. That's 1/4 of 4 pi, which is pi, which is pi, which is about 3.14. Right? That'll be that. And then the The area of the other crowd is 1/10, right? 36 out of 360. 1/10 of 4 pi, which is 2/5 pi, 2 pi over 5, which is about, we'll let the calculator do that. 2 pi over 5. 1.256, 1.26? 1.26 square inches. That is part C. That is part C. Part B, part A. Okay. Let's go to number 40. How do you see it? The outermost edges, oh geez. The outermost edges of the pattern shown form a square. If you know the dimensions of the outer square, is it possible to compute the total colored area? Explain. Yeah. I don't know if I'm supposed to do it. Yeah. I kind of want to do it too. But I want to I'm going to figure this out. Give me a second. So what you'd have to account for is basically how many little arc guy things that are there, because these are quarters of circles and stuff like that. Let's say the whole thing, 1, 2, 3, 4, 5, 6, 8. Let's say that this length here is 8x. I mean, my explanation will be my math. My explanation will be me doing it. But yes, if these are both 8x's, that means each of these little guys are x's. That means that any of these radii is an x. So any of those quarter circle things, area of a filled region will be x times x, which is x squared. Area of a quarter circle region will be 1/4 of pi times x squared, pi r squared. So that's pi x squared over 4. Pi x squared over 4. Count number of filled and quarter circles and add together. Because I think that's all there are, right? There are filled circles. How many are there? Not filled circles, filled squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. So total area is 34 of these x squareds plus how many quarter circle things? 1, 2. Well, there should be 30, right? Because there are 64 total squares. So 30 pi x squared over 4. So let's keep working that. 34x squared plus 30 over 4 is 7.5. 7.5 pi x squared. I'm going to factor out x squared, and I get 34 plus 7.5 pi. So whatever x is, they said if you know the dimensions of the outer square. So whatever x is, the outer square is 8 times that amount. So you just have to be careful there. You'd have to divide that by 8. So x is the length of 8. So let's say the outer square length was 16. X would be 16 divided by 8, which is 2. So you do 2 squared times that stuff, and you figure that out. So yes, you can get that stuff. This is 1/8 of outer square edge. If you know the dimensions of the outer square. All right. Hope that's making some sense. All right, let me pause for 1 second here. Okay. Number 40, I forgot where I am. Number 41. A circular pizza with a 12-inch diameter is enough for you and 2 friends. I don't know. I eat a lot of pizza, dude. That's not enough. That's not enough. All right. You want to buy pizzas for yourself and 7 friends. A 10-inch diameter. And by the way, actually, before I keep going on with this thing, this is how I sometimes evaluate my pizza stuff. It's like, how many dollars per square inch or whatever am I getting from a large versus extra large? I'm like, I want most bang for my buck. And you could do this at a pizza place. You can do this at a pizza place. Anyway, a 10-inch diameter pizza with, and that's not what they're asking. Oh, yes, they are. A 10-inch diameter with one topping costs $6.99. And a 14-inch diameter pizza with one topping costs $12.99. How many 10-inch and 14-inch pizzas should you buy in each situation? Explain. First situation, you want to spend as little money as possible. This is kind of interesting and fun, but it's making me really hungry. You want to have 3 pizzas, each with a different topping. Spend as little money as possible. You want to have as much of the thick outer crust as possible. Oh, wow. As much of the Oh, in a pizza, you assume that the, like, if this is a 10-inch pizza, the outer crust is like 1 inch. In the 14-inch pizza, it's still 1 inch kind of thing, I'd say. They don't give you more crust inch with a larger pizza. So, okay. So, a circular pizza with a 12-inch diameter is enough for you and 2 friends. That's 3 people. So, pi r squared, 12-inch diameter. So radius, see, the only problem is color coding all this. So what I want to do, let's put this as blue, just so we understand what we're talking about. Because I don't know how to label this. I could do this on my own with scratch work, but I'm talking to you guys about it. So radius is half of 12, which is 6 inches. The area of that pizza is pi times 6 squared, not rounding anything, which is 36 pi square inches. So you and your friends, this is the part I'm trying to figure out if it's like we each eat the same amount, but that's 12 pi, because we're dividing by 3, 12 pi square inches per person. I think the idea is that we all average eating this amount. I don't know if that's quite used yet, but we'll see. You want to buy pizzas for yourself and 7 friends, so that's 8 people. My guess is, with that in mind, I don't know if this is right, my guess is we want to cover enough area for that. You want to buy pizzas for yourself and 7 friends, so we need to be greater than 12 pi times 7, or 84 pi square inches for all 7 friends, for 8 people. That's how I think this is working. We need to make sure we exceed 84 pi. I feel like that's a part of what they're talking about. A 10-inch diameter pizza with 1 topping costs, this is going to be a lot to talk about, costs $6.99. So what I'm immediately thinking about right now is how many dollars per square inch or how many inches per square dollar or whatever I'm getting out of that. And I forget which way you want to say the rate. I think dollars per square inch. But the area for that one is pi times 10 squared, which is 100 pi. Did I say square inches per dollar? I said dollars per square inch, right? So that's 6 rate is $6.99 per 100 pi square inches. Now I can round that later, but that's inexact. I guess we're not including tax. And what color am I going to use? Because it's teal. A 14-inch diameter pizza with 1 topping costs $12.99. So each of these have 1 topping. I thought there was going to be more stuff with the topping stuff. Area is pi times 14 squared, which is, and normally a larger pizza is better value. You just want to figure out how much more value you get. Is 196 pi. So that rate is $12.99 over, sorry, I gotta keep going. 196 pi. I know we might speak on dollars per square inch, but just keep in mind you want to minimize the number of dollars per square inch when we do this. For the sake of humor, or to humor myself, for the sake of humor, for the sake of comedy, to humor myself, I'd like to see what those are about rounded. So 1299, excuse me, let's start with 699. 699 divided by 100 pi nets you two. This is a good deal. I just realized this is a fantastic deal, by the way, no matter what you do. 2.22 cents per square inch. And $12.99, hopefully this is cheaper. $12.99 over 196 pi. Now, this isn't per slice. No, this is per square inch. Still a fantastic deal. I just realized a 14-inch pizza at Round Table's like $40. Well, not one topping. Okay, it might be like 25 or something. It's still a great deal. Yeah, so this is a better value, 2.1 cents per square inch. And you're like, oh, what's the difference? I mean, it adds up. It's different. It's different. You're trying to evaluate and compare them. Basically, actually, let me say this. What if you multiplied this by 100 pi? If I multiply this by 100 pi, this is how much I'd be spending. I'd be spending $6.63 instead of $6.99. So I'm getting that better value, basically. How much better value? I'm actually, I'm overdoing this problem right now. I am saving 5% of my cost. I don't know. Anyway. Okay. What am I going to do with this information? Because this is an interesting problem as far as even the next parts. How many 10 and 14-inch pizzas should we buy in each situation? I feel like we need to exceed 84 pi. Where was that information? Right here. Must exceed, I think. Must exceed. I feel like that's a part of this. Okay. You want to spend as little money as possible. In that case, must exceed, but you want to get close, meet. Must meet. How about that? You want to get as close to this as possible without going under. So, part A, you want to spend as little money as possible. I want to get as close to 84 pi as possible, but buy as many 14-inch pizzas as possible. The good news is, wait, what? Hold on. A circular pizza with a 12-inch diameter is enough for you and 2 friends. You want to buy pizzas for yourself and 7 friends. You want to buy 84 pi square inches worth of... Oh, you know what? I screwed up a lot of this problem. These were diameters. These have to be divided by 2. Oops. At least I still spoke on this stuff. This isn't much. I mean, I don't have to redo the entire problem. But I just got to make sure I divide these by 2. So this is 49 pi. I was like, wait a minute. None of these are going to exceed our values at all. So this is 49 pi. You're probably yelling at the screen the entire time. I'm just having a conversation with this problem in general anyway. I'm very fascinated by this, and I'm very hungry suddenly. As far as the cost goes, I think it's going to be close to the same, if not the same, as what we were talking about before when it comes to value. But the value's not as good anymore. I mean, it's still great from what I said about like round table beats and stuff like that. Okay, anyway, let's go back to this. You want to get as close to 84 pi as possible without going over, and you want to spend as much money on basically this 49-inch square inch pizzas as possible, the diameter stuff. So here's the thing. Let's play with this a little bit. If I doubled this, if I'd got 2 14-inch pizzas, 49 pi times 2, that's 94 pi square inches. That's 10 pi square inches toward there. If I did 49 pi plus 25 pi, that's 74 pi, so 25 pi. I think your best bang for your buck, because anything you do, you have to exceed 84 pi. If I did 3 10-inch pizzas, that's 75 pi. That's not enough. 4 of them is 100 pi. That's more than 94 pi. So is 1 14-inch and 1 14-inch, 1 10-inch is 74 pi. Still not enough. So 1 14-inch and 2 10-inch is 99 pi. Still not enough. So this is your best bang for your buck here. You're spending the least, and you're getting the closest to your 84 pi area. I think that's what this has to do with. So you want to get two 14-inch pizzas. I'm explaining everything verbally with this, but basically it's cheapest, it's exceeding 84 pi, and by the least amount. Part B, you want to have 3 pizzas each with a different topping and spend as little money as possible. I don't know what the different toppings part has to do with this. I don't know what the different topping thing has to do with this. They're all one topping pizzas, right? A 10-inch diameter pizza with one topping, a 14-inch diameter with one topping. I don't think the topping thing has anything to do with it. They're just giving you a situation. But 3 pizzas. Spend as little money as possible. For 3 pizzas, let's compare. I think there's only one option here. Because three 10-inch pizzas is 75 pi. That's not enough. But one of these and 2 of those would be cheapest. So I'm just going to say it straight up. One 14-inch. I don't know why I only boxed the 14-inch pizzas. I should say 2. One 14-inch and 2 10-inch pizzas. Now, I didn't come up with these costs. You just multiply it, right? It's just, this would have been $24.98 for the $25.98, and then whatever. Part C, you want to have as much of the thick outer crust as possible. So in this case, this is where I think you're getting, it's not about money spending. I don't know. I think you don't want too many leftovers. So I think you want to buy 10-inch pizzas this time. Money is not relevant. So, and you need to exceed 84 pi. So you need to buy 4 of those. 4 10-inch pizzas. Because that'll give you 100 pi, square inches. And then cost is not relevant there, but the 10-inch pizzas get you more outer crust with that in mind. That was a really interesting problem, and I can't guarantee that I got it all right, but I think that's just the idea that you want to do with that. That just makes most sense to me. Okay, so my explanations were verbal with that. That's what I'm going with. I'm going to move forward. Let's go to number 42. You know that the area of a circle is pi r squared. Find the formula for the area of an ellipse shown below. Oh, I was thinking about the equation. I was saying, how am I going to introduce this to you? That's a long proof. The equation of an ellipse and a graph. No. They want the area. Okay. If I recall, okay, I think it's as simple as this. If we do pi r squared for this, and they're showing you the diagram to kind of help you out. Pi r squared, you think that this is r and this is also r in that case. So when I think pi r squared, I'm thinking that r times that r. So when I'm looking at this ellipse, and this is major axis, or half the major axis A, half the minor axis B, which is what they're called, I'd say that that's pi times A times B. Just kind of straight up like that. It's kind of like, because if both of these were the same length as r, then you'd multiply those r. So I think that's it. All right, number 43. And I can't guarantee that, but I think so. Number 43. Multiple representations. Consider a circle with a radius of 3 inches. Complete the table where x is the measure of the arc and y is the area of the corresponding sector around your answer to the nearest tenth. What's nice here is we can kind of just build that relationship once we find one of them. So you have a circle. Radius is 3. Okay, so I'm going to copy and paste that table. I'll probably just get one of them and just build off that because the 60-degree one is double. In the 90-degree one is triple the 30 and stuff like that. So come on. 30 over 360 for this first one. We're going to take 30 over 360, 1/12 of pi times 3 squared, 9 pi. 1/12 of 9 pi. Oh, can I write them? Yeah, to the nearest tenth. I was going to say, can I write them in terms of pi? I guess not, but 1/12 of 9 pi is 3/4 pi, 3 pi over 4. So let's go ahead and do 3 pi over 4. 3 pi over 4. And I'm getting 2.356, whatever. So here's what I'm going to do. So this is 2.4 square inches, right? Y is the area. Okay, so let me show you my calculator for a second. Y is 2.34 square inches. For 60, I'm going to double. Well, here's what I'm doing. I'm going to store this answer, store this value. Let's call it Y. Let's call it Y. Let's double Y and I'm going to just show you this. Let's double Y for 60 degrees because it's double the thing. So that's 4.7. Notice I'm not doubling 2.4 because that would have given me 4.8. That would have given me rounding error. So I want to use exact rounding stuff that I can. 3Y is for 90 degrees. 3Y is for 90 degrees. That's 7.1 instead of 7.2. 7.1 square inches. Or 7.0, right? Yeah, the larger this builds, the more the rounding error will matter to not have that rounding error. Whoopsie. 4Y is 9.4 instead of 9.6. Yeah, this is totally changing over time. So it totally matters to not round early. It's the last time I'm going to say that, unless they ask me about it. 5Y is 11.8. This is for 150 degrees. And then 180 degrees, well, half the semicircle. Or, excuse me, half the circle. This should be 4.5 pi. 6y. 14.1. Okay, so I filled this out here. That's part A. Part B, graph the data in a table. It should be linear. This is x and y. So let's do that. Got 1, 2, 3, 4, 5, 6. X is degrees. So 30, 0. 30, 60. Yet I wrote 30. 90, 120, 150, 180. And then this is, reach about 15 here. So I can go by threes. How about that? 3, 6, 9, 12, 15. This is square inches. This is area. Okay, so 2.4 right here. Now 0 would be 0, right? But this should be linear, whatever I do. 4.7, kind of like there. 7.1, 7, 9.4, above 9 there. I should probably go over this way a little bit. 11.8, it's really close to 12. And then, I don't know if this is quite equal spacing. And then 14.1. So that should be a linear relationship. I mean, I did the best I could. It's not really to scale, but there you go. That's part B. Part C, is the relationship between x and y linear? Yes. Area sectors grow in proportion with area. Sector areas. I'm going to type this. Yes, sector areas grow in proportion. It's been a long day with arc measures. Linearly, I should say. And yes, because it looks like it is. And yes, because that's how I found them, right? I found them using a linear proportionality. I'll go ahead and admit that. I apologize for that. But it should appear linear. If parts A to C were repeated using a circle with a radius of 5 inches, would the areas in the table change? Would your answer to part C change? Explain your reasoning. Would the areas in the table change? Yes, because it's a bigger thing. Yes, but they would not be 5/3 bigger. They would be 5/3 squared bigger. 25/9 bigger. Each of them. Again, area, square of areas do that stuff. Would your answer in part C change? No. Rate would still be linear. Relationship would still be linear. Basically, I'd take the original one. Well, I'd take all of them and multiply by 25/9. Not rounded, of course, from before. Okay, 2 more questions. Number 44. Critical thinking. Find the area between the 3 congruent tangent circles. Just that little guy there. The radius of each circle is 6 inches. Let's copy paste that and see what's going on. It says critical thinking like this is a tough problem. Maybe it is. I have no idea. I'm going like, Actually, I don't think it is. Oh, maybe. I'm thinking. I might have to use the bathroom before I actually finish this one. All right. So the radius of each circle is 6 inches. I'm just going to put 6s. This is an equilateral triangle, all of length 12. There's a center there if that matters. I don't yet know if it does. I need to figure out how those circles are kind of like touching each other, intersecting with each other here. See, one of these, if I draw an altitude down here, it goes right down the middle in this kind of way. I wonder if that's important to this. I need to figure out I don't know. I think I probably will use the bathroom here shortly. I think I need to figure out how like inward this thing goes to cover a certain amount, because it's not like I can just take these square things right here and do anything with that. That doesn't quite help. There's some critical thinking involved here. I do have to use the bathroom though. It's been like a 2-hour thing. Let me use the bathroom. I'll come back to this. Okay. I thought about it while I was in there. My hands are still drying, so let me process what I was thinking about while I was doing it. We've got to find the area of the triangle, and we got to subtract the area of those sectors. That actually isn't too bad. I was thinking a lot differently earlier on with that. So that altitude thing I got to erase. Just let me dry my hands. So each sector, listen, it's an equilateral triangle. That means these are all 60-degree angles. So whatever 60, I'm going to process this with you out loud. Whatever 60 is out of 360. The area of that sector is, each sector is the area of each circle. And there are 3 of those sectors we're going to take out. So we're going to take 1/6 of 36 pi for each of them, and then triple that. I think that's 18 pi. We're going to take 18 pi out of, I guess I could then use that height again because I can find the area of the triangles here. So I will do the area of the triangle stuff in a bit, but let's save that for, let's just do it first. And it's the 30, 60, 90 triangle. So in this case, that's 12, right? This is 6. This is going to be 6 root 3 as a whole. So the area of the triangle bit, it's 1/2 area of base, 12, times height, 6 root 3. That is 36 root 3 squared inches. Okay, that's the area of the triangle. The area of each sector, let's kind of wipe everything out now and go back. The area of each sector, like this, and there are 3 of them that we're going to use eventually. We're going to take 60 out of 360, right? 1/6, because that's a 60-degree angle. 1/6 of the area of any of these circles, pi r squared, 36 pi. 1/6 of 36 pi is 6 pi square inches. The area of the blue shaded region, did they say shaded? The area of the, find the area of the 3 congruent, wait. Oh, between, yeah. The area that's shaded. I thought it said find the area of the 3 congruent tangent circles. I'm like, wait a minute. The area of the shaded region takes your area of the triangle minus 3 area of your sectors. So we're going to get 36 root 3 minus 3 times 6 pi, or 36 root 3 minus 18 pi. Okay, I'm going to calculate that. That should be it. 36 root 3 minus 18 pi. 5.81, about 5.805. So about 5.81 square inches. And that's my story, and I'm sticking to it. Okay, I think 45 is the last one. Yes, last problem. Oh, it's a proof. Semicircles with diameters equal to 3 sides of a triangle are drawn as shown. Prove the sum of the areas of the 2 shaded crescents equals the area of the triangle. Actually, doesn't sound too bad, but I got to think about what I'm looking at here. I'm definitely going to copy and paste that so I can talk about some things. Okay. I'm going to do like a I'm just going to do math on this stuff. I'm not going to do a 2-column proof or anything like that. We're going to have to label some things. I don't want to deal as often with fractions if I don't have to. So what I'm going to do is call these things like names. I'm going to give this like, for diameter's sake, let's see, I'll give the individual radii sake. I'll call this x, y, and z. Therefore, this is 2x, 2y, 2z, things like that. So the area of the triangle will be 1/2 base, if I call that 2x, times height, let's call that 2y. Half of 4xy is 2xy. So I need basically the area of this shaded region to end up being 2xy. Z is obviously not used in this. Z's relationship with x and y is such that z squared is x squared plus y squared. And I bring that up because anytime I have to use z, I can replace it with this. Or, excuse me, z squared. Z is the square root of x squared plus y squared. I imagine that'll be used because this circle, semicircle, I need to take out of here, which means I need to use that portion in it. So what's the area of this circle? This area of that circle, I'll say small circle, area small circle is pi times x squared. The area of what I'll call the medium circle, because here's the, well, I'll say big circle, not the white one, is pi times y squared. And the area of the, oh, but that's not the semicircle though. So let's say 1/2 of this, 1/2 of that. And the area of the white circle is 1/2, because it's a semicircle, pi times z squared. Now z squared is also square root of x squared plus y squared, which when I square it, okay, I guess I don't need this part. I just need the z squared, is x squared plus y squared. So if I take this semicircle plus this semicircle and subtract, oh, that's not the whole thing though. Oh, subtract this and add the area of the triangle again, then I get the area of the triangle back out. Now that's interesting because can I use that in its, I guess I can. So the area of the, not the area that's shaded, right? I just want the area of this section. I'll just call that A, the area of that section, right? Prove the sum of the areas of the 2 shaded crescents equals the area of the triangle. So I need to use the area of the triangle in this, I think. I don't know if there's a way I can't do that. So the area, yeah, I think I have to. So the area of, I guess I'm calling it A. I'll call it, yeah, area, whatever. Area is, I got to do this semicircle plus this semicircle minus that semicircle plus the area of the triangle. So 1/2 pi x squared plus 1/2 pi y squared minus 1/2 pi z squared. There's more I have to say on that because that's x squared plus y squared. Plus, got to include the area of the triangle again, 2xy. Basically, this should wipe out and this should just become 2xy is really the point. I can factor out 1/2 pi, actually, yeah, I can factor out 1/2 pi from several terms here. Let me actually first distribute this part so we can make sense of that. 1/2 pi x squared plus 1/2 pi y squared minus 1/2 pi x squared minus, this distributes, 1/2 pi y squared. That way I don't actually have to do that, plus 2xy. These cancel, you're left with 2xy. Which matches what we had before right there. And that's just how I'm using the letters there. And it shows that they're the same. All right. And that's the last question. All right, guys. That ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. I was hoping this was going to be a shorter one, but it looks like some of the stuff really built. That pizza one really took into my time. It definitely took into my time. Hey, that'll do it for this one, guys. Take care. I'll see you in the next one.